colleague, Professor Rusch. So I guess I don't have to talk too long to you all about why all silicon photonics are interesting. Today I'll be focusing on a modulator, a Mach-Zehnder modulator, but of course what's interesting is being able to integrate other passive and active optical components on the same platform, and that we use widely accessible silicon foundries for this fabrication. And of course, because it's CMOS compatible, we can integrate these with other RF components, DSP, etc. So the advantage of using an all-silicon photonics solution is low cost, low power, and small footprint. If we look at previous demonstrations at 100 gigabaud for different modulators on different types of platforms, for instance, lithium niobate, indium phosphate, and silicon organic hybrid, there have been various demonstrations ranging from a raw bit rate per polarization from 400 to 600. But of course, these technologies are not all silicon, and so they cannot reap the advantages I discussed previously. If we look at demonstrations where all silicon modulators were used, we've seen demonstrations up to 85 gigabaud and various modulation formats, but they still have not reached a raw 400 gigabits per polarization. So what I'll be discussing today are our results where we transmit at 100 gigabaud at 32 QAM, giving us a raw 500 gigabits per second per polarization. So the modulator that we use is described in our Optics Express article when you are interested in more information. It's a unit-length design that with optimization. We use the IME AMF manufacturing process. The traveling wave modulator used in these results is a single drive push-pull with slow wave electrode. When we look at what is the challenge in pushing the bandwidth of our modulator, it basically comes down to two optimizations. One is in the operating point that we run in our modulator, and the second is in the DSP mix we use to compensate for it. Now, why is the operating point challenging in an all-photonic solution? It's because the bandwidth and the V-pi are intricately related in the silicon photonics, and the V-pi itself depends on the operating point that we choose to run at. So if I look at our previous results from last OFC, we used basically a linear equalization at that point, and we combined optical linear compensation. So we would, in this case, I'm showing illustrations for the 100 gigabaud 16 QAM. So we could use an optical preemphasis to compensate and flatten the spectrum before transmission. And in fact, what we do is we optimize the depth of that compensation by optimizing the mix of digital preemphasis and optical preemphasis. So this is similar to what we, a method we used in our previous demonstration up to 85 gigabaud, but now we're applying the same methodology at 100 gigabaud. We were able to move to the 100 gigabaud demonstration using some equipment loaned to us by Keysight. I want to acknowledge them. And now I have to go to the optimization of the bias point for this new demonstration at 100 gigabaud. And here we have the small signal frequency response at two different choices for the bias voltage. And at zero bias, we have 20 gigahertz 3 dB bandwidth, and at 2 volts, we have 30 gigahertz. So clearly, we can increase the bandwidth of our modulator. The problem is that when we change the bias, the operating point for our modulator, the V-pi is also changing. And so if we assume that we have the same swing available to us, I'm increasing the bias voltage to increase my bandwidth, but I'm also increasing my V-pi, which means that my modulation efficiency is decreasing. So I have to find a balance between these two effects. For that reason, we sweep the available operating point and look for a minimum in the bit error rate. And for 100 gigabaud operation, this happened at 2 volts bias. So just to compare that with our previous demonstration, when we were operating at 84 gigabaud, this balance actually occurred at 0.75 volt bias. So we can see it's important to do this optimization. Well, whereas previously we used only linear compensation methods, when we're operating at this higher baud rate, several nonlinear behavior come in. And it could be the modulator, it could be the RF amplifier. It's difficult for us to separate them, although even showing that this frequency response varies with the voltage, and our voltage swing is somewhere around 4 volts peak to peak, we can see there's nonlinear properties even in the modulator alone. So we then moved to a nonlinear compensation. So we looked at post-equalization. We had a 2 independent stages. In the first stage, we used a simple memory polynomial nonlinear filter, which was decision-directed. We only used first and third order terms. Then we did a second stage of post-equalization. And in the second stage, the motivation was to try and sort of overcome the situation we found ourselves in after the linear preemphasis. Of course, when we do this preemphasis, we're flattening the signal, but we're coloring the noise and enhancing the noise at the higher frequencies. So what we do at the second stage of the nonlinear post-equalization is that we have a low-pass filter to try and essentially whiten the noise, and we parameterize this alpha that we can sweep through to optimize. And in doing this, we may whiten the noise, but of course we're introducing intersymbol interference, but a structured intersymbol interference, which is well known to us. And therefore, the post-filtering is followed by a maximum likelihood sequence detection, very short one, the minimum length of one symbol memory. And so this combination of structured ISI, but a known structure that can be compensated by reasonable complexity, maximum likelihood sequence detection, gave us a nonlinear compensation method. We'll see that that was not enough, however, to get us into a good operating communications scenario. Therefore, we had to go into a nonlinear pre-equalization as well. And the pre-equalization we use is block-based. We use an iterative learning control with nonlinear adaptation. It was a hardware-in-the-loop adaptation where we did some frame averaging. It took about 10 iterations to get to convergence. So this is the experimental setup, which looks very similar to our previous demonstrations. The DAP, of course, was changed to now allow a 100 gigabaud operation. And to our previous demonstration, we added the nonlinear post-compensation and also the nonlinear pre-equalization. And the pre-equalization we do ahead of time, as I mentioned, hardware in the loop. This is the adaptation we did for the block-based nonlinear pre-equalization. So I'll start by looking at our 100 gigabaud 16 QAM results, and this is using linear only. So at 100 gigabaud, we're not able, or barely able to meet the 20% effect threshold. So we moved to a nonlinear post-compensation. The single stage gave us just below the mark, but not much. By combining the first and second stages of the nonlinear post-equalization, we were able to get well below the 20% effect threshold at 16 QAM. However, when we went to 32 QAM, we were not able to get below the effect threshold. And this shows why it's important to have added the nonlinear pre-equalization. So I'll start with the best we could do with the nonlinear post-equalization, first and second stage, and now I'll see how that compares with when we did pre-equalization alone. So we can see that the ILC nonlinear pre-equalization is giving us more robust compensation for the nonlinearity. However, when I combine the two, of course, I get my best performance. And we can see that at 16 QAM, I get a lot of margin at 100 gigabaud for my transmission. So here is the constellation for the 16 QAM, and if we take out the 7% effect overhead, that comes out to a 374 gigabit per second net bit rate on a single polarization. More importantly is that when we apply these pre and post nonlinear equalization to the 32 QAM modulation, we are able to come in below the 20% effect threshold. So in this case, going into the taking into account the overhead on this effect, we're able to get to 416 gigabits per second on a single polarization. So in conclusion, we've established that an all-silicon solution can rival data rates of more established integration platforms. We've achieved 100 gigabaud operation for 32 QAM, a line rate of 500 gigabits per second on a single polarization, and the bit error rate we achieved was 1.3 times 10 to the minus 2, below the 20% effect threshold, yielding, as I mentioned, a net rate of over 400 gigabits per second on a single polarization. In order to achieve these results, as I mentioned, we have to do two types of optimization. Optimization on the operating point, most particularly on the bias voltage, and then we also do DSP optimization, both in the linear regime, where we optimize across digital and optical linear equalization, and also in the nonlinear, both pre and post. I also want to acknowledge the funding we received from the Canadian NSERC organization. The device was fabricated using CMC Microsystems. Keysight lent us the equipment, and we have a collaboration with the UPT as well.